And now it gives me great pleasure to call up Justin and Ben. So Justin and Ben activity in software-defined networking goes back to beyond the dawn of time. The very early starts of software-defined networking before Scott Shanker even coined the term software-defined networking. The notion that we wanted to disaggregate functionality in networks, keep the switching layer, the forwarding layer very simple with typically logically centralized controllers that then would have a network-wide view and be pushing that down into the controllers. Ben and Jeff were working at Stanford at the time, both very instrumental at the early efforts to create the first SDN layers. Have continued that on through the years and are being recognized today for their work and their team's work in creating OVS, which is perhaps the de facto standard open virtual switch. Although VFP is in Windows, it's pretty good too. But certainly a huge amount of work has been built on top of their efforts, and that's why they're being recognized for this award. And today they're going to tell us a bit about their experiences and their thoughts on the directions going forward. And it gives me great pleasure, again, to be able to present them with a token of our esteem in the form of these plaques. And again, the real thanks to the community comes from all the great work that you've done. Thank you.
Thank you. So, yeah, first of all, I wanted to thank the program committee for selecting. I'm Justin, by the way, and this has been. Wanted to thank everyone for voting for this. It really means a lot to us, and we appreciate it. And so, while Ben and I are up here collecting it, it really is it's a big community project. So, we were early on, but we couldn't have done it without the hundreds of contributors to Open vSwitch. I don't know if there's anything you want to add. Okay. So first, I want to go over what is Open vSwitch, and I assume most people are familiar with it. But it's a as the name implies, it's an open source virtual switch, and it does the things that you would expect if you just run it in standalone mode from a normal switch. So it has the usual visibility, ACLs, QoS, port bonding, speaks all of the protocols. But really what makes it interesting and particularly relevant to this discussion is that basically every aspect of it can be programmed remotely. And the primary way to do that is through the OpenFlow and OVSDB protocols. And something that's less well known about the project is that we architected it in such a way that you can actually remove the forwarding part of Open vSwitch and sit it on top of other things like an ASIC, for example. So Open vSwitch is actually often used as a OpenFlow library for top-of-rack switches. So we know of a few projects that are doing that. We don't know all of them because of the license. People can take it. They don't have to let us know. But we do know of at least a few examples of people using it actually as their OpenFlow stack in top-of-rack switches. As I mentioned, it's all open source. It uses an Apache license. And everything that we do in Open vSwitch is out in the open. So we have a few mailing lists. All of the development happens on those mailing lists. So no patch goes into OVS without it having a public review and getting some sort of acknowledgement from somebody involved in Open vSwitch. And there are thousands of subscribers across those mailing lists. We've had hundreds of individual contributors from a variety of different companies. The structure of Open vSwitch, I think, maybe is a little bit unique in that we have what we call committers, and those are the people who are actually allowed to make changes to the code. So you can sort of think of it as the technical advisory board for Open vSwitch, and those committers are the ones who decide who else can become new committers based on their contributions to the project. And so any one of those committers can contribute to the project, or can actually commit to the project, and so they're kind of responsible for the final say about what can go in. And then those committers, spread across a number of different organizations. A year or two ago, we moved OVS into the Linux Foundation, so it's now part of it's a Linux Foundation collaborative project. It started off as a project from Nicira. I mean, it was always broadly contributed from a number of different companies, but we really wanted to make it clear that it wasn't a Nicira or VMware project, that it really is it's truly an open source project, and I think that moving into the Linux Foundation has helped that. One of the things that Ben is going to get into a little bit more is about a project called OVN that we started a couple of years ago that Similar to where OVS is a switch, open source switch, where we decided to actually create an open source application on top of Open vSwitch that does network virtualization. And one of the things that we've noticed since we started the OVN project is that we're starting to see a lot more contributors, which in some ways isn't surprising because it's being, we're moving up the stack. And so, not everybody is interested in sort of, working at the lowest levels of networking. And so, working at higher level constructs is probably a little bit more satisfying for a lot of people. And so we've seen quite a few new contributors to the project since then. So this is just, you can see there, quite a few contributors over the years to the project from a number of different companies. So I didn't want to spend a whole lot of time going over the history of Open vSwitch. I'll just touch on it a little bit. But Ben and I sort of wanted to focus more on things that we thought were interesting from being involved in this project for so long. And so the reason that Open vSwitch started was we were both in grad school. I was working with Martin Casado on the ethane, which became a lot of the basis for SDN research. And we decided to start a company around that called Nicira. But when we started Nicira, we weren't sure what we wanted to do. So ethane was a network access control system. We knew that we wanted to do something, and that we thought that this idea of doing something in a centralized manner was a good one. But we weren't sure network access control was the right application. So what we did was we built this open source system, and where you could do a centralized controller. And so we did an open source controller called Knox. And then we then started the OpenFlow reference implementation, and then used OpenFlow so that we could, where ethane was specific to doing network access control, we wanted to do something more general. So we defined the OpenFlow protocol. We started the OpenFlow protocol to do that. And eventually, about a year into Nicira, we started to figure out that what we wanted to do, which was network virtualization. But in the meantime, we had just built something that was very general and started working with the community and getting other people interested in it. And that worked out pretty well because once again, we didn't know what we wanted to build, but it was nice to build this platform that was fairly general, and we could then figure out the application to run on top of it. So OpenFlow, I think we can. I don't think it'd be too controversial to say that it's not a great protocol. We were sort of constrained by what we could do at the time. Some of that was...
I got in big trouble one time for saying it wasn't a great protocol.
Right. Right. So and in particular, that the comment that Ben had been making was, well, we kind of started working on this. We were hacking something together, and we thought that once we started getting all the other companies involved, that they would come in and they would have these great ideas, and it would would get cleaned up. But that's not usually actually the way that these projects work. So, there's a certain amount of momentum that's going in a certain direction, and so people aren't going to make huge substantial changes to it. And so it sort of kept going along that path. And so the OpenFlow protocol, when we were doing it, we weren't, at Nicira, we weren't sure what we wanted to do, as I mentioned. But one thing we were pretty sure we didn't want to do was to get into the switch business. And so the idea was that we wanted to be able to use hardware switches or software switches, but we needed to have a reference implementation. And so OVS actually started out as the OpenFlow reference implementation. We saw some architectural issues, and then we started over basically and came up with Open vSwitch. And but when we were designing the OpenFlow protocol, the hope was that we would be able to use something more, that we'd be able to use other switches with whatever the application was. And so the interface for OpenFlow looks more like an RPC to a TCAM than it does, for a programming language. And I think that goes to what the central problem with OpenFlow has been over the years, was this tension between the software folks and the hardware folks. And so if we were designing something for software, it probably would have looked a lot more like a programming language, like BPF. But we also needed to interface with hardware, which and those folks had existing ASICs that had interfaces that looked more like TCAMs. And so all the way through the OpenFlow standardization process, there's always this tension between the software and the hardware folks. And so and I think OpenFlow ended up being something that was a little too flexible for hardware and a little too inflexible for software. And so that brings up P4. So and I think OpenFlow was helpful for people to start thinking about developing networks differently. But the problem was that the hardware was pretty static. You had fixed tables, and whatever it shipped with, that's how you had to interface with it. And then between different vendors, between different ASIC vendors, and even in a single ASIC vendor, the different ASICs could look quite different, and you were stuck with basically how what that interface looked like. P4 has changed that, and so P4, and Cheng's going to talk more about that next, is describes a forwarding plane. And if we had P4 at the time when we were doing OpenFlow, I think OpenFlow would look a lot different. We would have had a lot more flexibility in terms of what we defined. However, I think OpenFlow was helpful to make people start thinking about doing more flexible hardware. And so one of the questions that we often get is P4 sort of OpenFlow 2.0? And I think in its existing form, it's not. So it's describing a forwarding plane that can be implemented, but it doesn't populate tables. I think that there's changes underway to add that so you can make it more, be able to control it from a centralized controller. But from my understanding, it's that ability isn't in the current version of the P4 specification. And then P4, we're actually looking at, even though it's targeted at hardware, we're actually looking at using it in OVS as well. And this is a project that Ben is involved in. There was the Pisces project, and we're sort of continuing along that path. We think that using P4 for the forwarding plane will actually be quite helpful. So right now, there's a ton of code in OVS that's responsible for parsing the packets. It's all written in C. It's all very ugly. It's possibly error-prone. And actually, the first talk, or actually the Best Paper Award winner, was related to a vulnerability that was found in that parser. And so we think that using P4 to define the parser in software will make it so that we can reduce the amount of code that C code being used to develop those parsers, so that it actually could be faster and also be more secure than what's currently in OVS. So while we were, when we started off doing the OpenFlow protocol for Open vSwitch, we had quite a bit of freedom to put what we wanted in because we were the original contributors to the OpenFlow specification. But then as OpenFlow got bigger, then there started being a lot of other companies that were contributing to it as well. And and so naturally that kind of slowed the ability to get things into the OpenFlow specification, which actually makes sense. But sometimes it was overly constraining to do what we need to do for our applications at Nicira. So we started adding extensions to OVS to add different, new capabilities to the OpenFlow specification. And so a lot of those features ended up being then later added to the OpenFlow specification because we were able to talk to people about what we did that worked well and maybe what didn't work well, and so we could provide some guidance. But with those extensions, we were able to add more general computation to the OpenFlow specification. So we had registers, we had control loops, and we actually ended up with something that, if it's not Turing complete, is pretty close to it. And so we had something that was much closer to a programming language that we could use to program OVS. And this has actually been something that's been very beneficial for what we've been doing for our projects. One of the things that happens every couple of weeks is that we'll have someone come in to Ben and I share an office. Someone will come in with some problem with a product that VMware sells called NSX, and they'll say, well, how does NSX do this? And Ben and I will say, in the forwarding plane, and Ben and I will say, well, we have no idea. And there's never a very satisfying answer for the other person. But I actually think it's really nice because when we have the controller team, which is telling OVS what we want to do. We have these sort of basic building blocks that they can build their own application on. They don't have to check with us every time they want to make a change. So even though we may have been involved in the initial discussions about what the design should look like, how they could optimally use OVS, things evolve over time, and they don't actually have to come talk to us. So we've had multiple major designs redesigns of NSX over the years. And we haven't really had to make any changes in OVS. Other forwarding planes that were more static, if there was a change, it had to go all the way down to the virtual switch. For us, we didn't have to change anything because the interfaces that we provided were fairly general. And then finally, I wanted to talk about OVSDB. And so OVSDB is a protocol that Ben designed a few years ago when we started to recognize that OpenFlow is very good for defining sort of ephemeral flow state. But there's certain things that you need to define that is much more slow moving. So for example, if you have a bridge and which interfaces are connected to it, you want that to survive over, over a reboot, for example. And OpenFlow doesn't really handle that sort of configuration. And so OVSDB was designed to hold that state, and then there was a JSON RPC protocol that was used to configure that. And so the combination of OpenFlow and OVSDB make it so that you can control basically every aspect of OVS remotely. But one of the things that changed over the years was that originally it was just designed to hold that sort of slow-moving state. But what we're seeing it used more for now is actually as an alternative to OpenFlow to do SDN programming. And this is something I meant to mention earlier, but a lot of people sort of conflate OpenFlow with SDN, and they're really not the same thing. OpenFlow is just a protocol to do SDN. There are lots of different applications, lots of different ways that you could achieve SDN without using OpenFlow. And we're seeing OVSDB being used more for that purpose, as just one example. And so the first time I saw that being used was when we wanted to work with top-of-rack switches. As I mentioned, those can be pretty static, so they have a certain TCAN that they expose. And we were trying to do network virtualization. And we would basically take the OpenFlow rules and we would put those into the ACL tables, the TCAMs that are provided on the NICs. But if you have a 48-port NIC and you have 4,000 rules, it gives you less than 100 rules per port. We couldn't even do just the most basic things in network virtualization with that. And so something that Ben and Bruce Davey worked on was this idea of, instead of programming things at a flow level, worked at a much higher level. We defined an OVSDB schema that would describe what we wanted to accomplish, how to do network virtualization, as opposed to how to do it at a flow level. And so you would say, for example, if something comes in on this physical port, put it into this tunnel and send it to this hypervisor. And that worked much better. We had multiple failed attempts of trying to make NVP and NSX, these network virtualization products that we worked on, work with hardware, and none of them were successful until we did that. And then that was actually a very useful mechanism to do that. And then actually the OVN project, which Ben will be talking about, we've taken that even further, and so we're actually using OVSDB to actually carry the flow state as well. So I just wanted to mention, just quickly cover the OVS architecture because it'll be relevant to the next slide. So there are three main components, the blue components of OVS. So on the left you have the OVSDB server, which is maintaining that sort of slow-moving configuration I mentioned, and that speaks the OVSDB protocol up to that controller up at the top. And then you have OVS vSwitch, which contains most of the forwarding logic, and that speaks the OpenFlow protocol, and that speaks that up to the control cluster. And then it gets its configuration from OVSDB server from those flows, and then it pushes it down to a data path, which is in many incarnations is run in the kernel. But that data path is really just a cache of recently seen traffic and does tunnel, incap, and decap. So we've really had this very modular system. We've sort of decoupled things, and that's had some advantages over the years.
Looks like I get to talk now. I've had a difficult week traveling, so if I fall asleep while I'm speaking, just find a quiet place for me and let me rest. So one of the principles that we've been using in OVS design over the years is trying to decouple things in smart ways. And Justin talked about that a little bit earlier, about how we have built several generations of network virtualization software at Nicira, at VMware, and now in open source as OVN. And none of those has required much in the way of changes to OVS. It's meant as a general purpose platform, and when you're designing something like that, you always wonder if you're doing it well enough. But I think that the success with these applications on top of it shows that we at least did an adequate job. So I'm pretty proud of that. And of course, outside of the ones that we've been involved in ourselves, there have been any number of application platforms and applications built on top of Open vSwitch that didn't require changes to it. On the other hand, I do feel that it should be easier to change OVS, and the P4 work that Justin mentioned earlier definitely contributes to that. If we're successful with that, and I hope to be, then adding support for a new protocol or a new header, that sort of thing, should just be a matter of adding a few lines of P4 code when you build OVS. Another level at which we've decoupled OVS is the split within OVS between the OpenFlow layer, the protocol layer, and its interface to the data path below that. We've defined a data path layer that is in some ways similar to OpenFlow, but it runs at a lower level. It's sort of even more of an assembly language than OpenFlow itself. And we've been able to add protocols to OpenFlow, a lot of features to OpenFlow without requiring much change to that data path protocol. We've also been able to make changes actually on both sides of that split without affecting the other. So that seems like it's worked out pretty well. The overall design that we've done with the data path is very much a sort of a slow path, fast path design. When things fit the model that OVS optimizes for, then most of the real work, most of the inner loops happen in that fast path. And I'd say that a lot of the design work and a lot of the refinements over the years have been around recognizing what important applications tend to hit the slow path a lot, so that we can either make better use of the fast path or make tweaks to that interface to better support what the actual applications want from it. And we had a paper in NSDI a few years ago that talked about how we do a lot of those optimizations. Actually, that paper gets to what I think of as the core problem in Open vSwitch and software switch performance. I tend to think of a software switch as having three parts to it in the packet processing path. At the start of the packet processing, you're getting packets in from some physical or virtual device, and at the end of the path, you're putting the packets out to some physical or virtual device. I don't really consider those to be much of an OVS problem. Those are device drivers. So you have your Linux kernel, you have your hardware, you have your DPDK driver, you have your netmap interface, whatever. And so the problem of making those fast is the problem of the people who write those device drivers. The bit in the middle is making the decision about what should happen to those packets. And that is a packet classification problem, and it's the core problem of making a software switch fast. It took us a long time to find a good solution to this, but I wouldn't say that we have a perfect solution. And we're actually working internally on what I think of as a kind of a hybrid classifier that uses some of the best ideas from tree-based classifiers and from tuple space search classifiers that we've traditionally used in OVS. We have some interesting preliminary results that are so good that I don't quite trust them. But if they actually pan out, then I'm hoping to submit a paper for review later this year. So for years and years, Justin and I were just working on Open vSwitch. We weren't really working on a controller, but we would see people working on controllers, and we had a lot of advice, a lot of feedback for them on the way that we thought a controller should be written. And then eventually, we had the chance to put our money where our mouth is and write a controller ourselves, OVN. And this is the point when you find out whether you're totally wrong or mostly right. I'm pleased to say that I feel like our ideas have mostly been borne out. First of all, this wasn't really a revelation when we started on OVN, but early on in what I think of as the SDN era, there was this idea that for each new microflow, each new connection that came into the system, it was going to be acceptable to send a message to the controller to find out what to do with that. Known as reactive programming. This isn't really true. There are a lot of connections in your network, and they can come through very quickly. If you do that, then you'll eventually be unsatisfied. It might take you a long time because, in our experience, about 95% of traffic will work just fine this way. But then you hit one of the traffic patterns where you have very short flows, and you'll be very disappointed. The next principle that is a little less obvious, maybe, is that we actually don't think that centralizing the controller itself is always the best idea. Instead, what we favor is centralizing the data, and we in OVN use a database for that, and then distributing as much of the control as we can based on that data to, in our case, the hypervisors. Those hypervisors that have some intelligence and can act on things are a lot closer to the actual network traffic that needs to be controlled, and they also have a greater amount of context because they're running in a more specific location. In our experience, it gives you a better result. It also is better at working properly when there's a network partition and you can't access that central controller. And OVN works a lot like that. So that brings us to OVN. So OVN is a network virtualization system. I've been using that term a lot without actually defining it, and I don't think that Justin did either. But in our sense, anyway, network virtualization is when you simulate the attributes of a physical network, like, for example, switches, routers, etc., in a virtual network. So if you have a bunch of hypervisors and you have VMs that should be networked to each other over a complex topology, and you implement that topology in software instead of in appliances that actually intermediate in the physical network, then that's network virtualization. So, like I said, in OVN, we use databases in the middle of the network as the main means of coordination. And what those databases contain is all logical or virtual information. It doesn't have any information about the actual location of the entities like the VMs that they talk about. Instead, each of these local controllers that run on the hypervisors convert this logical information into entities that are physical for them. So, for example, a reference to a VM that's on that particular host, that particular hypervisor, would be resolved directly, but a reference to a VM on another hypervisor would be resolved to a tunnel that leads to that hypervisor and ends up at that VM. We found that this architecture works well, and it represents an evolution of several generations of network virtualization controllers that were developed at Nicira and VMware. So let's see, I'm about out of time, but let me mention some of the things that we're thinking about now. We're thinking about moving higher up the stack in a couple of different ways. One possibility is there's been a lot of buzz about systems that do switching at L7, like, for example, on URLs, and often used in controller systems, or excuse me, in container systems. And I have a lot of questions about whether this is an appropriate direction for Open vSwitch, but it's definitely of interest, and we're thinking about it. We're definitely looking at running on top of new platforms and new data planes, and we're often getting patches to extend in those directions, and alternate data paths as well, such as one built on BPF or perhaps on NetMap. Thanks. I'm sure that we couldn't have done it without many of the people in this room. Thank you.